I want to highlight something that I didn't have time to point out at the end of last lecture, and that is that in this dragging string calculation, the speed of the string. So this was the way that various folks got a handle on physics related to jet quenching, but by using a heavy quark and imagining that you, with your fingers, grab this heavy quark and drag it through the plasma. This is the boundary of ADS-CFT. Here's the string trailing down into the bulk. And this calculation is only valid if the speed, so this is the Lorentz gamma here. So if the speed is less than something. So if Lorentz gamma is less than something, which is written here, m is the mass of the quark. Now, what goes wrong if you try and push this calculation beyond where it is valid? There are two ways of saying this. The first thing is to say is that if you exert a force that's large enough to keep this quark moving at a constant speed, which breaks this limit, then your force is so large that you have copious Schwinger pair production of quark-antiquark pairs. And so you're no longer talking just about one quark here, which you've grabbed with your fingers. All of a sudden, the string is breaking freely, and you're making lots and lots of quark-antiquark pairs. The calculation is broken down. That's the way that these folks put it. Another way of saying how the calculation breaks down is the following. In jet quenching, in the real story, there is no pair of fingers moving the quark along. What you're interested in is a quark with no external forces on it, but just decelerating due to the presence of the medium. So then you can ask, OK, let me try and get around what I just said by let's say at time 0 the quark is moving with a velocity that breaks this limit, but then have no force. So it's going to slow down. It'll decelerate. But what you find, and this is something we pointed out, what you find is that if you break this limit, so if you're on this side of this divide, then it's decelerating. It's decelerating so rapidly that it radiates. You can estimate how it radiates, as I'm going to talk about in a second. And that radiation also serves as a drag, because it's losing energy due to radiation. And this velocity cutoff here is the limit, not cutoff. This velocity divide is the velocity at which the deceleration due to radiation exceeds that due to drag. And, oops, what just happened? Oh, I guess I need power for the computer. That's what I need. To the left of this divide, which is a divide it's a relation between velocity and quark mass. To the left of that divide, you have a sensible description in terms of a quark being dragged through the plasma, or decelerating due to a drag force. To the right of that divide, that's where you have jet quenching and the jet quenching parameter. There's a comparable divide down here if you consider two quarks with a string between them moving through the plasma at this speed or this speed. This side of the divide is where the string world sheet is space-like. This Wilson loop is e to the minus real. It's e to the is, but then s is imaginary, so it's e to the minus real. And this is where you're describing jet quenching and Q hat. This over here, this is different physics. This is a slowly moving pair of quarks, or a quark-antiquark pair. In this case, the string world sheet is time-like. The Wilson loop then is e to the ite, where t is the time duration over which you look. And this describes screening and the screening length. And in fact, that's what I'm going to talk about in a few minutes. So there's this divide in the physics here, which had not been appreciated before these calculations were done. Who has a question? Yes?
So in the case when there's a vacuum, the velocity is greater than the speed of sound.
Mm-hmm. All of it. Let's assume that the mass is large here. So this divide can be far, far above the sound speed. So you can have supersonic motion that's in this regime. No problem. That's another place where physics changes is the speed of sound, but that's not what that is quite distinct. Okay, so I'm going to now I'm using this slide as an introduction to today. I'm going to do two things. First, I'm going to describe jet quenching is like with respect to jet quenching, we theorists are like the blind man and the elephant. Jet quenching as an experimental subject has many facets. There's transverse momentum broadening, there's energy loss, there's heavy quarks, there's light quarks, there's jet shape observables that I haven't talked about. And different theorists have tried to get at different pieces of it using different approaches. And I want to try and give you a sense that there's more still to be done. I'm going to describe another approach which has not yet come to fruition, but which might turn out to be interesting. So this started out with a calculation by this group here, which includes myself, where we were trying to see we set ourselves the following challenge. This dragging string calculation is sort of beautiful and simple to conceive. You're pulling a cork through the plasma, it trails a string. But we couldn't, in this calculation, get into a regime where radiation is important, where the acceleration and Bremsstrahlung is important. So we asked ourselves, what if we make the cork go in a circle? Now, nobody knows a way of doing an experiment where you grab a cork and move it in a circle. Okay, so this is a thought experiment now. And so there's a cork at the boundary, which is up here. It's going in a circle. It's trailing a string down behind it, which is trailing in a spiral. And what we did first, a couple of years ago now, was to just calculate the dEdt, the energy, the energy that's flowing down the string. The energy. So remember, I'm holding the cork with my fingers. I'm pushing it through the plasma in a circle. How much work am I doing? Okay, that it turns out is relatively. If you can solve the equations that give you the shape of this string, it's then an easy integral to compute dEdt. And I'm going to compare it on the next slide to two possible expectations. One is what you expect at low velocities is that if I'm moving the cork in a circle, if I'm moving it slowly, who cares that it's a circle? You should get the drag force. So at slow velocity, you should expect the drag force, and this is dEdt for the drag force. And then what might our expectation be if we move the cork ultra-relativistically? Well, in the v goes to 1 limit. Well, there's this beautiful and underappreciated calculation by Mikhailov, which shows that in vacuum, if you accelerate a charge in n equals 4 super Young-Mills theory, he used gauge gravity duality to show that the energy loss due to radiation, all he calculated was this dEdt, and he showed that it's the same as Leonard calculated for electromagnetism in 1897. This is synchrotron radiation, with the exception that the prefactor here, instead of being e squared over something, is square root of lambda over 2 pi. So this is what we would expect if I did this experiment in vacuum. We know the answer from Mikhailov. This is the answer. And what we find, so this is, ignore the way the vertical axis is labeled. This is dEdt for the actual calculation divided by dEdt for drag. And so down here at low velocities, you get drag. And this horizontal axis, omega squared gamma cubed, is chosen such that for Mikhailov's result, you get this straight line. And what you see is that there's a crossover in velocity where you go from being drag limited to being radiation limited. And there's this crossover. We even speculated that there might be destructive interference, because if you just naively add the drag deceleration and the radiation effect, you end up with above what the actual calculation gives. And there's lots of discussion, by the way, in the QCD literature of destructive interference between diagrams associated with jet quenching calculations. So we made that speculation. And you can then ask, when is the calculation valid? This is angular velocity omega. This is linear speed v, but plotted as gamma. And the calculation is valid below the red line. As you increase the quark mass, the red line moves up like this. You can see this is a lower mass, a higher mass. So calculation is good below the red line. The drag regime is below the dashed line. The radiation regime is above the dashed line. And you see that for a heavy quark, this circular motion calculation, you are in a regime where the calculation can be trusted and you are radiation dominated. So this is nice. We'd like to be able to do a calculation like this for linear motion, because that's what jet quenching is. You're moving fast enough that the dominant energy loss is radiation. And what we have right now is the jet quenching calculation, which I described at length yesterday, where you start in QCD, and then after you've isolated a certain gauge theory observable, you compute that in the strong coupling theory. But it would be nice, whether relevant to experiment or not, it would be nice to do a full calculation of that physics at strong coupling, and that actually doesn't exist yet. But this is as close as we got. But then, okay, that provokes you to ask, well, Mikhailov and we calculated dEdt, but is it actually radiating? So this is the picture that we'd like. This is a cartoon, not a calculation, but it's actually a cartoon that's very close to the calculation. So we then said, let's go redo this in vacuum, because vacuum is easier. So this is a cartoon now for the vacuum calculation. The string is going in a circle with a radius that's quite small on this figure. It hangs down into the bulk, spiraling around. And now there is a standard means. If you know the world sheet of the string down here in the bulk, you compute a bulk to boundary propagator and determine the energy density on the boundary. And so we wondered, will this energy density look like synchrotron radiation? So what is this is a well, we drew this diagram, but this could be in Jackson. The way synchrotron radiation looks, here is an electron moving in a circle, or here is a quark moving in a circle. It beams radiation in a forward-directed cone, which has a width alpha and a thickness. So this is a picture at one moment in time. This is where the quark is right now. It used to be back here. It used to be back here. It used to be back here. This is where the radiation is at this moment in time. This radiation was radiated a while ago. And it's a classic result from Jackson that alpha goes like gamma, and that thickness delta goes like gamma cubed in the ultra-relativistic limit. So that's what synchrotron radiation looks like. That's Jackson. Do we, from this calculation, get something that which looks like it? So we did the calculation, and this is the result. So this is now, these plots are in 3 dimensions of, these are plots in real 3-dimensional space. The ADS direction R is not shown. There's a quark moving on a circle of radius 1. Notice the plots go from minus 25 to 25. So the circle of radius 1 is a small circle on this plot. And this is a cutaway view in the equatorial plane, and you see a synchrotron radiation spiral. And if you then look on the sphere at radius 25, which is not quite the sphere at infinity, but anyway, the sphere at radius 25, you see this lighthouse spot, this beam of radiation. And if you look, this is velocity 1/2, this is velocity 3/4. The patch has gotten tighter, the beam focuses, and we in fact checked that the gamma and gamma cubed are exactly as they should be. So this looks like synchrotron radiation. And I should say, by the way, this, of course, making the plot is Mathematica did that for us, but the calculation is entirely analytical.
What's the driving forces?
Your finger. The driving force on the quark is, I postulate that there's an external agency. My finger is moving the quark in a circle.
But you didn't input any force term in the boundary.
Well, in effect, we did, because by requiring that the quark on the boundary is going in a circle where there's energy flowing down the string. So yes,
But that's a one particle, movement, right?
Yes, it's a one particle movement.
If I understand quark anti-quark rotation kind of thing, that is kind of the differential.
But this is a single quark. There's no antiquark in town. It's a single. It's an infinitely heavy test quark, which I am moving with my fingers. That's the calculation we've done. It's not a physical. It's not. We're not trying to do something that an experimentalist could realize.
What I'm saying is how put your finger into equations.
How we put our finger into equations? By fiat. I don't know if you know the word fiat. It means let it be so. We didn't describe some gauge fields which are exerting forces on a charged quark. We did not do that. We used the method of. So what? Someone had the method of staring at the equations. This is the method of putting in what you want to put in. Okay, and just to convince you that, so this goes out to a radius of about 3 periods, but we can go out farther in the calculation. So this is, think of a lighthouse beam. You are watching a lighthouse beam from a distance. You see a series of pulses, flash, 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 flash. This is the light at a certain distant point as a function of time, or actually the way we did it here, it's the light at a certain r as a certain angular position as a function of radius. And you see it looks like an EKG. And it looks exactly like what you see in Jackson, almost. If you look very carefully down here at, there's something funny going on right down here. So we pick one pulse, look right down at the bottom, and you see actually that the energy density is going negative. And by the way, I should say we're plotting here r squared times the energy density. It, of course, falls off like 1 over r squared. And this negativeness confirms to you that we've really done a quantum field theory calculation. In Jackson, the energy density is the sum of the square of things. It can't be negative. So we really have, by gauge gravity duality, done a fully quantum mechanical calculation, but the quantum effects turn out to be very small. Because look at them, you can hardly see them there. And we were amazed, I would say, by how similar this is to Jackson. Because think about what we've calculated. What we have here is a quark with a non-abelian charge in a non-abelian gauge theory. It's radiating gluons. Those gluons are themselves charged. And the coupling is strong. We're working in the lambda goes to infinity limit. So why, as these pulses propagate outwards, yes, their energy density is falling like 1 over r squared, but you would still think there should be some interactions. in Jackson, you understand this by saying photons don't interact with photons. But gluons do interact with gluons. Why are these pulses not spreading at all? And you can see in the equations that they're not spreading at all. To me, gauge gravity duality is sort of like experiment. You do a calculation, you trust the result, but it doesn't necessarily always tell you why things are the way they are in gauge theory language. And I think there's a puzzle here from the gauge theory side. It's very well understood on the gravity side. It's easy to understand on the gravity side. And all of these plots are analytic, as I said. And to make it even more striking the similarity, you can average over time, so this spot is sweeping around, and you can look at the polar angle distribution of energy density averaged over time. So north polar state equals 0, south polar state equals pi. Look at pick one velocity. I've forgotten what velocity this plot is drawn for. Pick one velocity and plot the energy density averaged over time as a function of polar angle. You get the blue curve. The Jackson calculation is the dashed line. It's not literally Jackson. If you look up in Jackson, you would get a slightly different curve. We had to redo the Jackson calculation because there are scalars being radiated too. So at weak coupling, we know what's being radiated. This is n equals 4 super Yang-Mills theory. At weak coupling, you're radiating gluons and scalars. But you can do the Jackson calculation for gluons and scalars, and it's the dashed line. And so this is an example of another piece of physics which changes hardly at all as you go from zero coupling to infinite coupling. Yes?
So could this sort of classical behavior be sort of a relic of the large N?
Yes. It absolutely could be. But it would be nice for that to demonstrate that, but yes. Lambda is infinity. So
the lambda is much smaller than 1, n is fine.
No, we did this in the large N limit at small Atoff coupling.
It's also done by gauge gravity. No,
no, it's done by Jackson.
You could do it for any n.
You could do it. This one we could do for any n. That's a good point. Did we look at this one as a function of n? I don't think we did. It would be simple to do. I just don't remember. Right, but the real question is that whether at smaller n the blue curve still agrees with the dash curve as well, and that we certainly don't know. Okay, so this is all a setup in the sense that this is an audience of theorists, so you should appreciate the fun of doing a calculation like this. But what we have now at our disposal is a lighthouse beam, and in n equals 4 super Yang-Mills theory there are no jets. This is a well-known result of Hoffman and Maldacena. They computed. Suppose you had E plus E minus scattering where the electrons coupled not to quark-antiquark, but to a fermion-antifermion of n equals 4 super Yang-Mills theory in the strong coupling limit. They calculated what would you see in E plus E minus scattering in such a theory. So E plus E minus, instead of going to QQ bar, goes to n equals 4 super Yang-Mills theory stuff. And the answer is you don't see jets. You see spherically symmetric flow of radiation, flow of energy at infinity. So there are no jets in n equals 4 super Yang-Mills theory. We're trying to study jet quenching. I've told you two ways of getting at that. One is heavy quarks. The other is the jet quenching parameter. Here's a third way. Now, you don't have a jet, but you have a flashlight beam. You have a lighthouse beam. So, if we make that quark spin very fast, it's a tightly collimated beam of energy. Now we want to do the same calculation at non-zero temperature. And we'll then see this flashlight beam of very high energy gluons, high energy relative to the temperature, plowing its way through the plasma and thermalizing. And we will be able then to compute. This will be a heavily numerical computation. We don't think we can do what I just said analytically. We will be able to see, in a numerical sense, the thermalization distance or thermalization time. Not for a jet. This is not a single parton. But for, it's the blind man and the elephant problem. You try different approaches. Okay. Today will be a lecture with several parts. Next part, I wanted to come back to the physics of screening. So I'm going to make contact here with experiments on J-psi mesons in heavy ion collisions. The J-psi is the CC bar, so a meson made of a heavy quark and heavy antiquark. But let me come at that from a theoretical point of view by first talking about screening. What is the potential between a static quark-antiquark pair, let's just do this for quark-antiquark pair at rest, in n equals 4 super Yang-Mills theory at zero temperatures? This was computed by Maldacena. It's one of the first computations, and it's Coulomb. QCD does not have a Coulomb potential. So this is unlike QCD at 0 temperature. But then you go to non-zero temperature, and these folks, again, more than a decade ago, these folks showed that this potential gets screened. So you compute the force between a quark and an antiquark pair, which are a distance L apart, and with that L is bigger than 0.277 over T, no potential. If it's inside this, there's a Coulomb potential. And this is not a bad caricature of QCD at high temperature. The screening potential can be computed on the lattice in QCD. And at 0 temperature, it's Coulomb and then linear. Okay, that's the continuous line here. The data points are lattice calculations at non-zero temperatures. These are low temperatures. This is a high temperature. This is 4 TC. This is 2 TC, et cetera. And what you see is it's Coulomb at small r, and then it flattens off. It does not have a kink in it. The fact that there is a kink here is an artifact of taking the lambda goes to infinity and large NC goes to infinity limits. In QCD, where everything is finite, you wouldn't expect a kink, and you don't find one. But you see Coulomb and then screened, Coulomb and then screened. So there's no sharply defined LS in QCD, but these authors define one anyway. You can make operational definitions, and they find an LS of 0.5 over T, which is not so different than 0.277 over T. But you don't need gauge gravity duality to study screening of static quarks. Okay, so because I learned yesterday that you hadn't seen how the Wilson loop calculations work, I thought I would run very quickly through my pedestrian understanding of how ADS-CFT works and how you get to use it to calculate things like a screening potential, because this also comes from a Wilson loop calculation. So as you will have seen, there's a dictionary between n equals 4 supersymmetric Yang-Mills theory, the gauge theory on the boundary, and the gravitational theory in the bulk. There's a dictionary that connects G squared and NC and on the gauge theory side, and G string and the ratio of R squared to alpha prime on the gravity side. And then the third entry in the dictionary is that the temperature on the gauge theory is given by the Hawking temperature of the black hole horizon on the gravity side. And I don't know whether Joe has already done this, but I want to give my intuition for what these limits are doing for you in the context of this specific calculation. So here's the calculation I'm trying to do. In the gauge theory, if I'm a four-dimensional physicist, I only know the green stuff. I have a quark and an antiquark. I build a supercomputer, do lattice QCD, compute the quantum fluctuations of the gauge fields in the boundary theory here, and determine the quark-antiquark potential after spending a few teraflop years of computer time. If I know about the gravitational theory, I realize that there's a string hanging down into the bulk that connects the quark and the antiquark. I extremize the energy of that string, just like the catenary problem, and I differentiate that energy, and that gives me the force. And this is a calculation which an undergraduate can do. You don't need teraflops of supercomputer time. Now, why is the calculation so simple? This is the point I wanted to make. The large 't-Hooft coupling limit makes the tension of this string large. And that means that the string is not fluctuating very much. And the large NC limit means that G string is small. That means that there aren't loops breaking off. So these two limits here, if you don't take these two limits, what you have down here is string theory. And that's probably just as hard to handle as the green stuff. But when you take these two limits, the beauty of gauge gravity duality is that when you take these two limits, physics on the gravitational side becomes very simple because the string theory becomes an undergraduate classical mechanics problem. And that's the whole trick. That's what Maldacena noticed. In my language, that's what Maldacena noticed in 1997. This is also a way to point out what this story would look like if you describe a confining theory with gauge gravity duality. So if you have confinement in your theory, in your boundary theory, then what happens in the bulk has to be the following. You pull the quark and antiquark pair apart, and when you pull them far enough apart, the string has to do this sort of a thing. And you can see that this is not scale invariant. There's a scale in R here, which I've picked. And this scale in R here corresponds to the string tension, which is a scale in the gauge theory. And so this is what should happen in a confining theory, but it does not happen in n equals 4 super Yang-Mills theory. The shape of the string stays the same as you pull the quark and antiquark apart. That's what gives you the Coulomb potential, which has no scale in it. And so this is a lesson that you should not use n equals 4 super Yang-Mills theory as a guide to vacuum QCD. But what about n equals 4 super Yang-Mills theory at non-zero temperature? So how did we get, or how did not we, how did these folks 10 years ago compute the screening length? Well, they did the same calculation. Quark-Antiquark pair connected by string, move them apart, find the extremal solution. And then when you get to L screening, you find, hey, wait a minute, I can't find any extremal solution which connects the quark and antiquark pair. The only solutions I can find are those which hang down to the horizon like this. And at this point, this quark here and this antiquark here are not connected, so you can move them apart without any force. So when L is bigger than LS, no force. The force has been screened. And then you do this computation, and it's this computation that gives you this 0.277 over T. And as I've already said, this is not a bad caricature of QCD at high temperature. And so this is, many of us have good friends who, when we tell them, good friends from the QCD community, who, when we tell them what we do, they object. How can you be using n equals 4 super Yang-Mills theory to describe QCD? And one of the points of today's lecture is I'm going to, over the course of the rest of the lecture, give you all my answers to that question. And probably the most important one is that n equals 4 super Yang-Mills theory and QCD are much more similar in the plasma phase than they are in the vacuum. And those friends who are asking you are probably thinking about the vacuum. Okay, so the payoff from thinking about screening is a prediction for experiment. And what Hong and Urs and I did was, on the gravity side, trivial. We said, let's compute the force between a quark and antiquark that are moving through the plasma with some velocity v. And the algebra is only a tiny bit more complicated. In no interesting way is it a harder calculation than what was done before. But this is now a calculation that you can't do with lattice QCD, because lattice QCD studies static questions. And this is now, although I haven't drawn it, I haven't tried to cartoon it here. Remember, there's a plasma in this plane. And this quark and antiquark pair are plowing their way through the plasma. And that is not something which, in any easy way, can be extracted from lattice QCD. Folks are actually trying. So it's not easy, but what you have to do is something like doing an analytic continuation from Euclidean to Minkowski. You don't literally have to do that, but it's close to that hard. And it's hard to do. It's very hard to do analytic continuations when all you have is numerical data. But they are trying. But for us, it's easy. So what did we find? Well, we found that the screening length. Did I show the function? Do I bring the function? No. Okay. The screening length, the dominant velocity dependence is that the screening length goes like 1 minus v squared to the 1/4. In other words, 1 over the square root of Lorentz gamma. There is a function of v and theta here, which is the remaining dependence, and this function is for all values of v and theta, I think it's between 0.8 and 1. So you can ignore it. To make an equality here, you need a small fudge factor. But then I got rid of it by putting a wiggle sign here. So after the fact, after you do this calculation, you can argue that this makes sense. But this is an after the fact argument. If the screening length is controlled by the energy density, then the energy density goes like t to the 4th. And the energy density as a function of velocity, the energy density is t0, 0, so that it Lorentz contracts like gamma squared. So if the screening length is controlled by the energy density, then you would expect the screening length to go like 1 over root gamma. But this is not a trivial argument, because why should the screening length be controlled by the energy density and not the entropy density? If I made this kind of an argument with entropy density instead of energy density, I would have gotten a different power. But anyway, it's a way of saying that this is not an unreasonable result, but it's not a substitute for the derivation. Okay, so now why is this of interest to heavy ion physicists? Well, there are mesons in QCD made of a heavy quark-antiquark pair, the J psi and the upsilon. So the J psi is CC bar, the upsilon is BB bar. And these mesons survive in the Quark-Gluon plasma. The argument is simple. A heavy quark-antiquark pair, that kind of a meson, is much smaller than lambda QCD. A BB bar meson is smaller by a factor of something like 3 or 4 than lambda QCD. And that means that to dissociate it, to make it fall apart, you need the screening length to be of order the meson size. So you need the screening length to become very short to dissociate this meson, and that means that the dissociation temperature is relatively high, because the screening length, remember, goes like the screening length here it is, it goes like 1 over the temperature. So what we've now said is that this screening length has a velocity dependence, not just a temperature dependence, and this suggests then that the temperature at which one of these heavy mesons dissociates will be lower for a moving meson than for a meson at rest, and lower by a power of 1 over root gamma. So you can think of this as a heavy meson in a Quark-Gluon plasma wind. Okay, if you look at this from the rest frame of the heavy meson, it's a meson in a Quark-Gluon plasma wind. So the title of our paper is Screening in a Hot Wind. So how do I connect this to data? What's the situation in data? In the data. So J-size suppression, J-size are the CC bar mesons. There's a 25, almost 30-year story of the measurement of J-psi mesons in heavy ion collisions. It was suggested more than 20 years ago by Matsui and Zatz that you could use the fact that these mesons don't exist above some dissociation temperature as a thermometer for the plasma. The simple cartoon 20, 30 years ago was, if you get above that temperature, there shouldn't be any of these mesons. And so this led to the phrase J-size suppression. This is a very long story, which I'm going to oversimplify. The reason it's a long story is that there are many ways to dissociate J-psi mesons. Achieving a temperature above T dissociation is just one way. They can also bump into things and dissociate. There are also nuclear effects in their production. It's a long story. But one way of looking at the present data is as follows. So here's the first part of the spectroscopy of J-psi. This is the ground state, and then it has a 2s and a 2p state. And it's an experimental fact from measurements really at Fermilab as much as anywhere else, that 40%, that at the energies we're talking about at RHIC, 40% of the J-psis you observe were actually produced in one of these states, and then these states quickly decay to this, and then you observe this in your detector. These two states are bigger, just like in the hydrogenic system. These are bigger states than this one, so these dissociate at a lower temperature. And in lattice QCD calculations that are still controversial, you find dissociation temperatures very close to TC for these bigger states and around 2 TC for the J-psi. This 2 TC is not established. Different groups argue about this. And then experiments have been done at both RHIC and the SPS, which SPS is lower energy heavy ion collisions at CERN in the 1990s. And they yield J-psi a yield between 100% and 60% of that in proton-proton collisions as a function of impact parameter. And I'll actually show you the data here. So this is number of J-psis seen divided by what you would expect based on PP collisions. And this is a cheat. This is a theorist's variable. These experimentalists should be and were castigated for plotting their data versus a rather massaged variable. This was their attempt to convert impact parameter, which is what this axis actually is, into energy density. They should have just plotted it versus an experimental actual observable. But anyway, when they did this, what they found is that the SPS points, which are the red ones, and the RHIC points are on top of each other. And other than this last RHIC point here, there's no data point at RHIC which is significantly lower than those at the SPS. And what I just said remains true even if the red points and the green points are not at the same horizontal position. So what does this say? It suggests that RHIC doesn't reach 2.1 TC. It suggests that both the SPS and RHIC are reaching temperatures of around TC and are dissociating these ones, but neither is dissociating this one. And then, so in other words, they're dissociating these ones, so you lose 40% of the observed J-psis, and that's consistent with what you see here. That the most loss you've seen is around 40% of what you start with. So then Hong and Urs and I make a simple prediction, which is you should look at J-psis moving with high velocity, large transverse momentum, at high enough velocity. If that CC bar pair, which would have become a J-psi, is moving through the plasma, Even though the plasma is not hot enough to dissociate it at rest, it's hot enough to dissociate it when it's moving. And we put in sort of toy numbers. We said, suppose we believe this lattice calculation that the dissociation temperature is 2 TC. And suppose we pretend that we know that RHIC reaches 1.5 TC, which is a reasonable guess, but certainly not well known. Then we predicted that somewhere around 5 GeV in transverse momentum, these J psis out here at high PT should be suppressed more. These should be screened. The potential out here should be screened. They shouldn't form. You shouldn't see J psis with these PTs. This story, as you can see, requires both our ADS-CFT calculation, which will, whether or not it ever proves relevant to heavy ion collisions, that calculation lasts forever, and a model interpretation of the current data in heavy ion collisions. That model is due to these folks, Karsh, Karzeev, and Zotz. And there's a lot of assumptions in that model. The lattice calculations are controversial, et cetera, et cetera. So we're in the perfect position as theorists. If this prediction is confirmed, we will declare victory. If this prediction is falsified, we'll blame it on these folks. So do I have the, okay, wait, data's coming. To go, this is what as far as we went, but to go from this to a prediction for data, I want to make another point, which is if you want to be really have an impact in this field, you need friends. You need friends who actually do the kind of phenomenology that the experimentalists notice, that sort of can make plots that experimentalists can take to the bank. For us, our friend was Urs Wiedemann in many of the things that we did. In this case, it's a Japanese group. I'll show you in a second. So what you need to do is you need to embed our nice calculation in a much more model-based framework for describing, first of all, you need the hydrodynamic expansion. And then second of all, you need to describe production cross-sections of the J psi as a function of transverse position, which that you can get from experiment. And then what you've got is a plot like this. This is J psi suppression, the actual experimentalist observable, as a function of impact parameter. And this time, this is the actual experimentalist observable. I won't explain this, but this is basically impact parameter. This is head-on collisions. This is peripheral. And this is integrated J psi suppression. No, not integrated. This is a particular, I think it's one of the bins out here as a function of PT. And this is the Japanese group I mentioned. And this is survival probability of the J psi without the hot wind effect, with the hot wind effect. And for the parameters that they put in, the drop happens at about 3 GeV PT. Notice that it's quite a significant drop. It's a big effect. The message of this is not the fact that it's at 3, but that the drop is big. They also made predictions for V2 of the J psi, which is something that, again, will in future be measured. So after you do these calculations, what you realize is that the PT at which the effect sets in is a very sensitive measure of the difference between the dissociation temperature at zero velocity, what I called 2.1 a minute ago, and the actual temperature that's reached. Because the smaller this difference is, the less velocity you need to push the J psis over the edge. So if you change T dissociation at zero velocity from 2 to 2.2, which is very much within the uncertainties of what we know from the lattice calculations, then this 3 GeV moves by a factor of 2. So we can't predict this 3 GeV with accuracy, but if it's measured, it will tell us something interesting. The interesting thing is you can compare copper-copper versus gold-gold. I won't talk about that, but it's interesting. Okay, what's the data at present? It's dominated by error bars, as you'll see. I'll show it in a second. Actually, let me show right now. I think I have it next. Yeah. So this is the data at present. This is the J psi suppression as a function of PT integrated over impact parameter, I believe. No. Actually, it's different for different points here. So these are different impact parameter selections for different points because this is low statistics physics. And what you see is that, if anything, it's going against our prediction. There's this one point here at 5 GeV where the suppression is, the number of J psis, the suppression has gotten less. So this is bad news for us. But then you see that these next 3 points have enormous error bars. So our attitude here is we want to wait for the data to get better. And this is a propaganda plot from the experimentalists as to how this is a promise for how small the error bars will be with what is called RHIC-2 luminosity. And RHIC-2 luminosity is a benchmark that, in fact, it's not like there's one machine and then another machine. There's a steady program of upgrades of luminosity, and RHIC-2 is a certain benchmark, which I think will be reached next year or the year after next. And this is the promised error bars for J psi yield as a function of PT once you get to this certain luminosity benchmark. There's actually data in the can that was taken a few months ago, which I think in some sense will be halfway in between the current situation and this promise. And in fact, it should be closer to this. So we're expecting a significant reduction in these error bars very soon. And also, as I said here, at the LHC, you can do upsilons. At RHIC, upsilons are never going to be, you might discover an upsilon at RHIC, but you're not going to be able to do much with them. There'll be very few of them. But upsilons at the LHC will allow you to compare upsilons to J psis. It'll allow you to do various ratios that will make it, there's systematic effects in here that I haven't talked about that you'll be able to cancel out if you have the upsilons also. So, this is the propaganda plot from the LHC experimentalists. This is what they say their error bars will be on the ratio of upsilon prime to upsilon with one run year. I should explain what a run year is. The LHC will run 1 month of every year with heavy ion collisions. So one run year here means 1 month. But it's 1 month at design energy and design luminosity. And neither design energy nor design luminosity will be achieved this November. So this is not a promise for this November. This is a promise for a couple of years from now. They were also pessimistic here. For the experimentalists, if you're trying to dig out an upsilon, you find an upsilon by upsilon decays into mu plus mu minus. You have to find those tracks. The more other tracks there are present, the harder that task is. And when they did this simulation, they assumed 2,500 charged tracks per unit of rapidity. And this is high relative to most expectations. So actually, they were pessimistic in this sense, but they were optimistic in the sense that they used design energy and design luminosity. So we shall see. Okay. I think, what time is it? So I have half an hour, right? Okay. So I will just advertise and then skip that. The calculation I've described so far was of a screening potential. Test quark, test antiquark, calculate the force between them, make those test quarks move, calculate the force between them. But you can also study mesons in gauge gravity duality, real mesons. You have to do a lot more work. Has anyone ever mentioned D3, D7 system? Was it mentioned last week? A little bit. I'm not planning to do it. Anyway, for those of you who have read the literature, you introduced D7 brains. You could actually compute meson spectra in its n equals 4 superdiagnosis theory with fundamental matter added. All the groundwork was done by these other authors. What we did was to show that for these mesons, we reproduced the result that they only exist at a temperature which is less than a certain dissociation temperature, and that dissociation temperature depends on velocity, where the dominant velocity dependence is 1 over root gamma. And this is, again, a fudge factor f of v, which ranges between 1.01 and 0.92. So it's basically 1. So we showed that the inference that we drew from analyzing a static potential is verified when you do a much more sophisticated calculation in which there are actually mesons in town. Hong and his student Tom Faulkner then showed in another calculation that these mesons actually have widths, and that these widths start to blow up. They blow up like k squared, beginning at a momentum k at which this velocity. I need one thing here. I need this plot. The way to think about this, I said that there's a dissociation temperature which depends on velocity, but you can turn that on its side. At a certain temperature, there's a critical velocity above which you don't find mesons. So you sit at one temperature, go up, you hit a critical velocity. You hit at one velocity, increase the temperature, you hit a dissociation temperature. So you can think about this result either way. And well, just for fun, I'll show you how the way you get a curve like that when you have a theory with mesons in it is you compute dispersion relations. And look at that. This is a dispersion relation with a velocity which is less than the speed of light. And that gives you then, as you increase the temperature, the limiting velocity drops. Okay. And what Hong and Tom showed is that these mesons have a width, which is a non-trivial statement, because this requires going slightly beyond the lambda goes to infinity limit. And this width starts to blow up at a k at which the velocity reaches that limiting velocity. So again, this indicates that the way these mesons are supposed to not survive, and one of the ways that you can see that they're not surviving is that their width starts to blow up. We also, for fun, did this for baryons made of heavy quarks. So we did a screening calculation for NC quarks in a circle and showed that when there's a screening length for that too, and that screening length also depends on velocity with the same 1 over root gamma. So I'm trying to give you a sense that because we can't, this is another answer for your friends in the QCD community, it's true we can't do exactly the calculation that we want. But you try and get the same underlying physics in many different ways and see whether the picture that you get out, the insight that you get out, survives, whether it's robust against being probed from different directions. That's another thing that we folks need to be doing. Okay, so skip. Here. So I want then to, I'm trying to leave myself with 20 minutes after I end. So I want to end the penultimate part of my talk by summarizing the differences between n equals 4 super Yang-Mills theory and QCD and sort of giving you a sense of what I think about them. First of all, as I've stressed, the two theories are much more similar in the plasma phase than in vacuum. But they're not the same. So to make the insights that you gain from these calculations semi-quantitative, I think what we have at the moment are insights. But to make them semi-quantitative, we need to take steps towards QCD on each of the axes with respect to which the two theories differ. So one difference is in the degrees of freedom at weak coupling. So if I define nu, the number of degrees of freedom, by energy density as nu times pi squared over 30 times c to the fourth, then in QCD, nu is a count of the gluons and the quarks. It's 47.5. And notice that, as I mentioned before, that when NC is 3, this is 16, and this is almost 32. First of all, there's two differences here between QCD and n equals 4 super Yang-Mills. There's the difference between 47.5 and 120, which is the count for n equals 4 super Yang-Mills theory. And there's the difference between the fact that here everything is in the adjoint, and here there's actually more, in a weak coupling count, there's more degrees of freedom in the fundamental representation of the gauge group than in the adjoint. So what you need is observables that are insensitive to these differences. And we know of one for sure, which is 8 over s. And maybe q hat over the square root of nu might be insensitive to this, but this is a perhaps. And in particular, for those of you thinking of things that you'd like to do, getting away, going to higher order than 0 in NF over NC, number of fundamentals over number of adjoints, is important. But the answer that I give to my friends who worry about this is, first of all, that at high, I didn't put this on the slide, but I should say it, at high temperature, bosons and fermions, there's no difference between a boson and a fermion. So the fact that the theory is supersymmetric should not worry you at high temperatures. The fact that it's a plasma and a supersymmetric gauge theory as opposed to a non-supersymmetric gauge theory has no important consequences as far as I can see. Adjoint versus fundamental, that you should worry about. And the real reason why I'm not too worried about this is that liquids have no quasi-particles anyway. And all of this counting is a counting of quasi-particles in the weakly coupled sector. This 8 over s is, to me, what it teaches us. Well, we know it reminds us that liquids have no quasi-particles, and it teaches us that for a liquid, maybe all this stuff is not so important. But it would be nice to get at this in other ways. Okay, next difference is that we are working in the 't Hooft goes to infinity limit. In QCD, the coupling is not infinite. And here there has been progress. The 1 over lambda, the leading 1 over lambda corrections have been computed for 8 over s, and there's turned out to be small at the kinds of lambdas that we're interested in. They've been partially computed for q hat. As you can see, there's something to do there. What about conformality? This we already talked about. N equals 4 is conformal, QCD is not. But once you get above 2 TC, the lattice calculations in QCD are rather conformal. So somewhere, QCD must become weakly coupled. But maybe there's a conformal window starting. The interesting thing is it starts just a little bit above where RHIC is right now. So if this picture is correct, the LHC should be a better place for all this physics even than RHIC has been. On the other hand, if we in this community are unlucky and the LHC shows that V2 drops at the LHC, indicating that the plasma has become weakly coupled already at 3 TC, then those of us interested in Quark-Gluon plasma need to go back to perturbative methods, which we would be happy to, but you would be disappointed. I'd be disappointed too. But anyway, perhaps there's a strongly coupled conformal window in QCD. We don't know how high up in temperature it goes. And one of the lessons is you can't use thermodynamics to tell. What I will say here is that in studies to date, adding a level of non-conformality as in QCD thermodynamics to N equals 4 Supercomputer theory has no effect on 8 over S and little effect on Q hat. But this is something that deserves much further investigation. And then last of all, and worst of all to me, is the NC issue. N equals 4 Supercomputer theory require 1 over NC squared taken to 0. And I'd have no problem with this if people had calculated the 1 over NC squared corrections. The large NC approximation in QCD is very well respected. It's used in many places in QCD. It had nothing to do with gauge gravity duality. It goes back to a Tuft in the 70s, and it's been used in many places. All the places where it's trusted are places where the first 2 and even 3 powers of 1 over NC, like what Subir was talking about with the epsilon expansion. In statistical physics, you do an epsilon expansion. You want to use it at epsilon equals 1. The reason the places you can do that are the places where somebody has computed 6 orders and then done Borel resummations. There are places in QCD, like heavy baryon spectroscopy, for example, where people have done 2, I think even 3 orders in powers of 1 over NC. I'm thinking of work by Manahar and Jenkins and others. And so there you have a sense that you can trust it at NC equals 3 because you've seen the corrections. But for that's not true for any of the things I've talked about. We don't know whether the corrections are 10 over NC squared or 1 over NC squared. And this, I think, and this is a hard problem because it requires actually doing string theory instead of just classical gravity. So this is something for you and not for me. But this, I think, in terms of the place where there's really a big payoff from the string theory community for solving a hard problem, this is one. Okay. There's a long list of things that I didn't have time to describe even with almost 4 lectures. Some of them, there's Taliotis on here somewhere, so you can hear about them from Anastasios in his talk. So others of them, I can't do everything. Meson spectral functions, Son could tell you about this if he chooses. And actually probably the thing with the most names up here, which I didn't get to, although Taliotis should be in there, yeah, he is. What you'd like to do is simulate the collision of 2 pancakes. And as Anastasios can tell you, there are shockwave solutions in that you can describe, and you can try and study the collision of 2 shockwaves and look for the formation of a black hole in the final state. And that black hole is a sign of thermalization. And this is something where is he sitting? He has made some progress on analytically in simple settings. There are other groups trying to do what I just said literally, which is a numerical problem. Anyway, so there's lots of things going on that I didn't have time to describe. Whoops. What did I describe? Sorry. Well, I'll highlight 5 insights that I think you can take to the bank. First of all, thermodynamics within 15 to 25% of that at weak coupling arises at strong coupling. That's a very important lesson. It says you can't use thermodynamics to tell whether you have a weakly coupled gas or a strongly coupled liquid. Second of all, 8 over s of 1 over 4 pi in these limits is true for any gauge theory with a gravity dual. 8 over S in the QCD plasma, for which I didn't show it, but there's some early evidence from lattice calculations, and there's lots of evidence from RHIC, which I discussed at length, and 8 over S for the unitary cold atom gas seem comparable to this 1 over 4 pi. That's really the insight that got this whole business started. Q hat, plugging in numbers is fun, but the thing that you can really take away is that it's proportional to the square root of S, not S. For an infinite class of strongly coupled plasma. So jet quenching doesn't count gluons. And then when you put numbers in, you get numbers that are a little larger than the perturbative calculation, but still smaller than what people currently extract from data, but we should just wait. In a strongly coupled plasma, heavy point-like quarks drag, diffuse, and excite a Mach cone. They behave like bullets in water instead of like electrons in water. And heavy quarkonium mesons, CC bar, which are bound above TC, they dissociate at some higher temperature, T dissociation, and that dissociation temperature drops with velocity. So these are qualitative insights, and I think the real payoff to my field from these calculations at this moment are qualitative insights like this. I've described some of the challenges that people need to work on in order to make these semi-quantitative. I'm going to skip here. Yes, what to watch for? Well, from RHIC, charms and bottoms. They're putting in vertex detectors. They will be able to actually see charm and bottom mesons. J size at higher PT. Identify jets and their modification. Study jet shape observables. This is coming. The medium response to jets. This is still murky right now. And the thing I want to talk about in the last 17 minutes is the search for the QCD critical point. So I'll talk about that after I finish this slide. What about the LHC? So you wouldn't build the LHC just for its impact on heavy ion collisions. Okay, the LHC is a however many billion euro machine. RHIC was the discovery machine in heavy ion collision physics. RHIC was the one that took a big step across the threshold into a new phase of matter. The LHC is expected to be the discovery machine at the electroweak scale in proton-proton collisions. So this is not the physics of condensed matter-like systems. This is the physics of single particle collisions. But we all hope at the LHC in PP collisions you'll discover qualitatively new physics. The Higgs would be the least interesting possible discovery, and there's a whole host, as you all know, of many much more interesting discoveries that may happen. On the heavy ion side, we get the LHC sort of for free. It's being built for those motivations, and it can do heavy ion collisions. So the management at CERN decided it was worth investing in detectors, in making sure that the detectors could do heavy ion physics. So that has been done. The first thing that's going to come out is a measurement of V2. That will happen the first day. The data from one day of heavy ion collisions at the LHC will give a good measurement of V2. One day of data and probably 1 month of analysis. I know this because at RHIC, the very first data on V2 was shown at a conference about 6 weeks after the first collisions, and it was based on 20,000 events. And if you look at that old plot, it exists. You can look at it. The error bars are bigger, but the physics is there. So 20,000 events is much less than a day. But then the big story at the LHC, which will take more than a day, is jets. Jets up to 200 GeV, studying their modification. The theoretical control of all the calculations I described will be much better, and so will the experimental understanding. J size and upsilons, as I mentioned. From theorists, and the ADS CFT side, more QCD-like gauge theories and more dynamical backgrounds. That's what I put on the slide. You guys can come up with other ideas. From the phenomenologists in the heavy ion community, they are working on three-dimensional viscous hydrocodes. That's actually pretty well under control now, but just within the last year. And studying jet quenching in three-dimensional viscous hydrocodes, or in the material described by a three-dimensional viscous hydrocode. This is the kind of thing which groups of people are working on right now. I won't talk about lattice. Okay, so I wanted to end. I have 15 minutes. Originally, I thought I'd give a whole fourth lecture on this, but I'll just give you a quick look. To me, the most interesting thing that is going to come from heavy ion collisions right now, in data that has been taken within the last 2 months, is the search for the critical point. So this is not data. This is a cartoon. This is a cartoon from some document prepared by experimentalists. I'm going to dim the lights so you can see everything on this. Can you see the yellow lines a little better now? They're still hard to see. So this is the phase diagram as a function of t and mu. And you do a heavy ion collision, you land here, you expand, you cool, you freeze out, and here are the freeze out points. So these black dots are from data. Okay. And this is speculation. So they put a critical point right there, a line of first order transitions right there. We don't know where this critical point is. What you can tell, the idea of this plot is to show you that as you go to lower and lower collision energies, where you land on the phase diagram moves down and to the right. We discussed that already. Labeling these with collision energies is speculation, but it's sort of it's informed speculation. And what has happened in the last 2 months is that data has been taken for the first time at RHIC at root S of 7.7 and 11.5 and 39. And what's going to happen next year is data will be taken at 27 and 17.3. So in this cartoon, and root S of 200 is up here. That, of course, we have billions and billions of events. So, and in fact, we already have at 130 also. So after next year, there will be data at all of the energies shown in this cartoon except the lowest one. And so what you'll then be able to do is scan in root S, which means scanning in mu. Was that too much? I think that'll work for all slides except this one. So you scan in root S. That means you're scanning left to right. You're moving the freeze-out point left to right on this phase diagram, and you'd like to see evidence for this critical point. And so because I have 15 minutes instead of a lecture, I can't walk you through how you go from thinking about the Ising model to thinking about critical fluctuations of the order parameter to thinking about pions and protons. But what happens when you do that is that you realize, you discover it, so I'm quoting here Stefanov from 2008. There's a history that goes back before this. That the critical fluctuation, so at that critical point, you just like in the water-steam phase diagram, you have long wavelength phase transitions at the, long wavelength fluctuations at the critical point. What's fluctuating is the order parameter, which here is a linear combination of baryon number and the sigma that we talked about in the sigma that he called the Higgs. If this were the electroweak phase transition, it would be the Higgs that was fluctuating. And so you then have to work out what the event-by-event fluctuations of that order parameter do to pions and protons. And you get fluctuations from event to event in the numbers of particles, in the number ratios, in momenta. And the magnitude of those fluctuations all go like a correlation length squared. This was known going back to 1999. What Stefanov realized in 2008 is that you can look at higher non-Gaussian moments of these distributions. And the skewness and kurtosis of distributions goes like correlation length to the 4.5 or even to the 7th power. So they are very sensitive to the presence of long wavelength fluctuations. And the understanding of how the sigma couples to pi pi and sigma couples to pp, in any effective description of QCD, there will be a sigma pi pi coupling, a sigma pp coupling. This one actually occurred in one of Sabir's talks, and this one, in a sense, occurred in another when he introduced fermions. But these are effective couplings, not fundamental ones. And so there are uncertainties in these coupling constants, big G and little g. So the idea then is you're an experimentalist. You do 5 million events at square root of S of 7.7. In each event, you count the protons between eta of 0 and 1. You then make a histogram, number of events versus number of protons. This is a histogram of the number of protons in the event. And you measure the width, the variance, the mean, the variance, and the higher moments. And so I'm going to use quote results in terms of the kappa 2, which is the mean of n squared, mean of n cubed. Instead of mean of n fourth, you subtract this quantity in the standard way so that you get something which is 1 for a Gaussian. 1 for Poisson. not 1, equal to the mean for Gaussian or Poisson. Okay, so then you need to put in a correlation length. And in the results that I'll show you, this is not a calculation. This is a guess. This is a reasonable guess for if the critical point occurred at a mu of 0.4 GeV, so 400 MeV, which actually I think is roughly where they put it on, the experimentalists put it on this cartoon. Yeah. And there's a reason for that. If it's at 0.4, it'll be in the data that's just been taken. But nature might not put it there. And so I have to tell you about the location of this peak, the height of it, the width of it, and the shape. So the height, what controls the height, if you sit right at the critical point forever, the correlation length is infinite. We put 2 Fermis, 2 Fermis is not infinite. The reason we have this peaking at 2 Fermis is because what happens in a heavy ion collision is not you sit there forever. It's that you cool down the phase you cool on the phase diagram with a certain cooling rate. And we estimated about 10 years ago what's the largest correlation length you can get given how fast you cool. It's limited by what's called critical slowing down. And the kinds of estimates that you see in the literature are sort of range from 1.5 to 3 Fermi. 3 Fermi, I think, is out. So we picked 2 Fermis. But this is controlled not by static thermodynamic physics, but by dynamics, and therefore it's poorly known. What about the width here? This width, if you had lattice calculations at non-zero mu, you would be able to learn something about the width. So over what range of mu is the correlation length larger than 1 Fermi, say? We don't have lattice calculations that are good enough to do that yet at non-zero chemical potential. The issue is finding ways to evade the sign problem. So it's not easy, but people are working on it. And so these widths are taken from model calculations, and let's call them guesses. The thing which you can say is that there's nothing in the physics that says that this width should be small on QCD scales. So you can see it's of order 100 MeV for the red one, of order 200 MeV for the blue one. There's no reason to expect tiny spikes with width of 1 MeV. And the shape comes from Ising model critical exponents. We actually did a reasonable job on the shape. Okay, so you then take this correlation length and run it through the calculation of the 4th moment of the proton distribution. You take kappa 4 for the proton distribution, divided by the appropriate number of powers of n to make it volume independent, and you get an amazingly large peak. This is the seat of the 7th effect. So you get omegas going up. Omega is this dimensionless ratio, volume independent ratio goes up to 400. That's if the coupling between sigma and protons is 7. If instead it's 5, you get 100. Now, do I have the data on the next slide? Yes. So is 100 or 400, is that big? So let me show you what is known in the data. So this is collision energy. This is mu. These are 3 existing energies where there's data. There's good data here and here. There's low statistics data here. This is basically our omega 4. It's not exactly the same. They didn't do exactly what we think they should, but it doesn't matter for this talk. And it's 1. 1 is what you get from Poisson. If you have Poisson distributed observable, this quantity is constructed such that you get 1. And these open symbols here are the predictions of various cascade codes. Cascade codes here do a good job of describing the uninteresting physics. They have no phase transition in them. They have no critical fluctuations in them. They have billiard balls in them. But there are other ways of getting fluctuations. For example, from resonance decays, which the cascade codes do a good job of describing, leads to small effects in this observable. So the one way of saying it is that the data is right on 1. If, in fact, the data had turned out to be at 1.4, nothing interesting would have been concluded. And now you go back and look at the predictions, and they're at 400 or 100. Okay. So if you see anything like this, you will know that it's interesting. And to give you a sense, again, so we put the critical point by hand. We put it at 0.4. If you go back down and look at the lower mu's where there is data, you will see that for these parameter choices, they shouldn't have seen anything at the energies, at the mu's at which they've looked so far. And there's data on tape which goes out to here. well, at sort of one energy which corresponds to this mu, and another energy which corresponds to a mu that's around here. Data taken for the first time within the last 2 months, not yet analyzed, or at least not yet publicly talked about to me. And this is the fourth moment of the proton distribution. Well, you can do other observables. You can do the third moment of the pion distribution. That's the red one. Here you can do the third moment of the proton distribution. That's the red dash one, blue one. You can do the fourth moment of the pion distribution. That's the green one. You can do you have two distributions. You can look at correlations between number of protons, number of pions. You can do sort of the mean of two, the average of the number of pions squared, number of protons squared. That's omega. This is all as a function of chemical potential.
Omega is a moment as a function of what as a function of what?
Well, let me do like one which is just say 4 pi. You take the histogram of the number of pions in a million events, and you look at the shape of that distribution.
Histogram as a function of what?
Number of pions.
Oh, right. Okay.
Number of pions in the event. What's fluctuating is the number of pions or the number of protons in a slice of the event. You can see you can make lots of these observables, and there are lots of uncertainties. So now you start making ratios to try and eliminate uncertainties. We sort of we think of it as there being 6 things that are uncertain. There's the proton density. Some of these observables depend on the proton density. There's the coupling of sigma to pions, the coupling of sigma to protons. There are 2 universal ratios. So for Subir, in the Ising model, there are these lambda 3 and lambda 4 quantities which tell you how things vary as a function of angle around the critical point. Which tell you it's the effective coefficient of sigma cubed and sigma to the 4th, and it's known how they depend on the correlation length. But then there's a prefactor which is angle dependent in the phase diagram, and which is known for the Ising model. But the mapping of the Ising model onto the QCD phase diagram is uncertain. So there are uncertainties here. And then, of course, the fundamental one is the correlation length itself. But we have many, many observables, so you can take ratios. And there are 4 ratios which you can't read. There are 4 ratios that we've constructed that are independent of all of these. So here are those 4 ratios.
So in all this, you're measuring properties of the static Ising model or one of the Halpern-Holmberg dynamic universality classes?
The answer is that when we estimate how large the correlation length can grow, so the way we are thinking about this, we will lump all of our dynamical ignorance into the question of how big can correlation length grow. This is all static. But when we estimated that, we used Halpern-Holmberg with the correct Z, which Son was the first one to figure out which was the correct chapter of Halpern-Holmberg to read. Okay, so these 4 ratios, one of them is the ratio of the skewness of the proton distribution to the skewness of the pion distribution. One is the ratio of the kurtosis of the proton distribution to the kurtosis of the pion distribution. And then there's 2 other ratios that involve these mixed correlators. And by construction, all of them are equal to 1 for critical fluctuations. And for Poisson, they are very different from 1. In fact, 2 of them are 0, 2 of them are large. So the way you use these ratios, I think it's the way I did it. 2 of them are 0, 2 of them are large, because n pi is larger than np. So the way you use these ratios is if you start to see these cumulants peak, so you start to see significant deviations away from Poisson in the shape of these distributions, then you calculate these ratios. And if you're in a regime where you're dominated by the interesting physics instead of by Poisson fluctuations, these ratios should all go to 1. So this will be a way of telling that the physics, anything away from Poisson will be interesting. But this will be a way of telling that interesting physics is related to the critical point. And as you should also be able to guess, if you measure lots of these observables, you can then extract lots of the parameters. It turns out you can't get the number of the proton density you can get in other ways. There are 5 uncertainties that you can only get at from this physics, and it turns out you can constrain 4 of them from these ratios. There's lots of ways of doing it, but one way of doing it is to constrain these 4 combinations, and each one of them can be constrained with several different observables. Okay, so I didn't make a concluding, the real conclusions to the main part of my lectures was 20 minutes ago, but I wanted to give you a sense that there is something interesting maybe about to happen in heavy ion collisions, or not. You know, if nature puts the critical point at a mu of 600 MeV, it will not have been found in the data that was taken in the last few months, and nature may well do that to us. That's why we do experiments. As far as I know, the physics I've just described in the last 20 minutes, there's a lot of connections to condensed matter physics. That's for sure. I don't see a connection to gauge gravity duality, so that's why I left it to the end and gave it short shrift. And I will stop there.